Hello everyone, my name is Charlie Romine, and this is lab number 2 for Physics 21 or 2211 on free fall and drag, and also sort of Newton's second law. So introduction, our goals are to illustrate Newton's second law or the momentum principle, and looking at how F net is the sum of the forces acting on an object, and also to discuss how drag affects an object falling. The physics ideas, for starters, F net is the summation of the forces with forces in opposite directions having opposite signs. So this means that when you add up all of the forces, both the positive and the negative forces, you get the output force or the net force. We also will discuss constant forces such as gravity, where it's almost always 9.8, and just is consistent, or in the non-constant forces like drag that change throughout the operation. Springs are another good example of a non-constant force. So for my experiment, my initial conditions, I dropped a piece of paper, a crumpled up piece of paper, so it had more drag than a rock, as the lab instructions said. The system, in this case, is the paper. The surroundings include the air that the paper is falling through, and not really much else, because not much affects the paper during the experiment. So yeah, here's the sort of the important part of the code, the stuff that I actually had to change. So to start is the no drag code, so the model without drag, just the straight force of gravity model. The B value is 0 because drag is defined as our B coefficient, which you just kind of had to find through experimentation. At least that's what I did. That's what my TA told me to do. And then times velocity squared. So this first model, we ignore F drag completely because you multiply by B and that line above that little red arrow. So that's totally not existent. So it's just the vector of the force of gravity in the negative direction or going downward on the ball of, or not the ball, it says ball, but it's the piece of paper that I dropped. Then in both codes is this little red box where we use the velocity update formula and the position update formula with a very small delta t to get a fairly accurate tracing of what the paper should do as it falls. Then we jump over to the other side with the with drag code. The B value I found to work best for my experiment was 0.0135. And then the only real difference here is that the F drag component of B times the velocity of the paper falling squared is used and subtracted or added to the force of gravity, and it's working in the up direction against gravity. So as for my sort of results graph, here's this. The orange line is the no drag model. So what it would do if drag was non-existent, if air resistance wasn't a thing. That is how this paper should have fallen. And you can see it goes much faster because there's not a force acting upward, so it's accelerating faster. And then the blue line is my actual results from the test, from the data I found in Tracker. And then the gray line is the experimental model with drag. And as you can see, they're fairly close. The paper fell in, I tracked it in Tracker, and it was pretty close to what actually happened. But as you can see, there's a less acceleration in the negative direction when drag is a factor. Error sources, the paper spun as it dropped, which led to inconsistent drag force. Not that the drag force is consistent, but as it rotated, it changed the shape of the body being pushed on by the air. So it led to a less consistent drag force than you would expect. And then again, the tracking, as in Tracker, is done frame by hand, and sometimes it's hard to find the reference point and be super exact with that. So that can lead to small deviations, but still deviations nonetheless. What does it mean? Looking at terminal velocity. Terminal velocity, as it says, is when force of drag and force of gravity are opposite of each other and equal. This leads to a net force of 0, so there's no acceleration, and the object will continue falling at whatever velocity it is currently falling at. For the what if, I've got two graphs here from computational models I mocked up, and talking about how if an object is thrown down, would the terminal velocity be higher or lower, and would it reach it faster? So as the models below show, when you actually throw, for it to do this, I changed the initial velocity vector in the code. So when you throw it downwards, when you just drop it, it eventually reaches a terminal velocity of about 1.8 meters per second. And when you throw it, it actually reaches a terminal velocity less than that. I don't know if that's just my computer model being weird, or if that actually happens, but it should reach about the same terminal velocity, but it should do so faster because the force of drag is going to remain the same. as it equals gravity on an object. But if you throw it downward, it should just get to that point quicker. So yeah, that's pretty much it for lab number 2. Thanks for watching.